Good morning, everyone. The work I'll be presenting is primarily the work of our collaborators, but I take full responsibility for translating that information and data into a wonderful Prezi that you all can enjoy. And so BioWorth is the work of my advisor. She's the co-PI, and hopefully you enjoy this Prezi. So our team consists of collaborators across disciplines within WSU, from the biological sciences to economics to biosystems engineering, as we mentioned, civil engineering. But outside WSU, we also collaborate with people from the Pacific Northwest National Laboratory. You'll hear from Ruby in a few minutes, also Oregon State University, people from UC Santa Barbara, as well as people from on the East Coast at Clark University in Massachusetts. And so the area of interest is the Columbia River Basin, and so it has plentiful resources. You can see that forests, grasslands, and croplands, and also air, water, and land. And there are multiple land use and ecosystems in this area with agriculture, forests, and grasslands, as I mentioned. But there's also projected temperature and precipitation changes that will exacerbate current water quality and quantity problems. There are multiple in and out of stream water uses, and there are other intensifying issues like fish and wildlife, tribal considerations, and the increased need for renewable energy. And so what is BioWorth doing? And it's trying to move forward this idea of integrated environmental modeling. And so we're taking standalone models from their particular disciplines and integrating them to behave like a single unit. And so what we can do is we can couple different parts of the Earth system, such as the atmosphere, the land, and water, also with human activities, with the human system, and couple them together. And so here is finally a schematic of BioWorth. And our overarching goal is to develop an understanding of the regional decadal scale carbon, nitrogen, and water interactions in the context of global change to better inform management decisions in the natural and agricultural context. And so you can see from this diagram, we can do that by linking atmospheric, terrestrial, and aquatic processes also with human decision-making and economics. But it's more than just linking, it's actually capturing the coupled feedbacks between these different systems. And so, we can do that between different Earth system processes, like here we have hydrology, biogeochemistry, your carbon and nitrogen cycling, with also some atmospheric chemistry and meteorology, and also economics, and you have your nutrient and sediment transport, but also reservoir operations and stream flow routing. And so the basic question we want to answer is, what are the unintended consequences of a particular management practice or policy that aims to provide for our needs while still sustaining our natural resources? So some inputs into this regional Earth systems modeling framework in our different sectors, as we call them. So in cultivated agriculture, we can look at different crop selection, irrigation, fertilization. In our rangelands, we can look at the effects from grazing. In forests, we can look at thinning. Water resources, we can look at the effects of water rights, which is very important in the Columbia River Basin, as well as reservoirs. Water quality, we can look at nutrient management. Air quality, we can look at emission regulations and pollutants, and also exogenous agents. So essentially, by having detailed management-related model inputs, you can get decision-relevant outputs. So here are some example outputs from my fellow graduate students and our other collaborators, as well for our different sectors. So first, we'll delve into the cultivated agriculture, irrigation systems, and water resources. And so this slide shows the changes in regulated supply and demand for the Yakima River Basin, which is Washington's largest agricultural economy and the 5th largest in the nation. And so you see here historical supply and demand. Supply is in the black lines and also the dotted lines, and you have future supply and demand into the 2030s. And demand is the green bars. And so you can see that in the future there will be more unmet demand here, as you see. And it's important to keep in mind that these are regulated flows, and so the reservoirs are taken into account. And so the reservoirs can't really buffer this demand, as they are already included in the model. And this next graph shows the year 2030 projected impacts on the Washington crop yield for both dryland and irrigated crops. So for example, the effects due to changes in temperature, which are in the bright red bars, are primarily negative, except for winter wheat right here, which may be taking advantage of the warmer temperatures in the cooler months. And so the take-home message from this slide is that the responses due to changes in the climate are very complex and also very crop-specific. And so you see we list very specific crops here. And so for this reason, we use a very sophisticated crop model that can include these competing factors for different individual crops. This next slide shows the spatial distribution of potential changes in crop yield due to climate change and carbon dioxide impacts. And so from mostly positive changes for non-irrigated winter wheat, we go to mostly negative changes, impacts on sweet corn in the bottom right. And so this primarily shows the capability of BioEarth to consider the different crops and their responses spatially. And it's important to note that the apples show kind of neither positive or negative impacts, and that's primarily because there's a management load function included in the model. And so we'll move on to rangelands now. And so what we're trying to do here is incorporate management into an ecosystem model. And so we're using Reyes, which essentially integrates water, carbon, and nitrogen cycling at the watershed scale. And with this, we're looking at how management of grassland, rangelands, such as grazing, affects biogeochemical cycling. And so what we can look at is how different grazing periods might affect the recovery period of biomass, seen here in this graph to the right. And along that same line, we're currently looking at the issue of upscaling. And so there are currently two approaches to land surface hydrology modeling. We have a top-down approach, as you see here on the left, which uses the VIC model, the Variable Infiltration Capacity model. And that's a very large-scale land surface model. It's very rich in representing the water and energy fluxes. And so it's very detailed in the vertical sense. And so that makes it very amenable to coupling with atmospheric models, since it also operates on the grid scale. Conversely, Reyes is more of a bottom-up approach, and it operates on the watershed scale. And that is able to capture the lateral movements of water and nutrients between the different watersheds and patches. And so what we're doing is we're upscaling Reyes to capture the hydrologic conductivity, which governs the water, carbon, and nitrogen cycling. But while Reyes is needed for that, we still need to upscale with aspatial patches, as you see here, using some approaches from the VIC model to reduce computational requirements. So in forest, here's an example of thinning, and essentially thinning has the potential to offset reductions in annual streamflow due to warming. And so you see the black line is the baseline streamflow, while red is the streamflow with 2 degrees Celsius warming. But then the blue and green ranges show the streamflow for with thinning. And this is work done by our collaborators at UC Santa Barbara. In terms of air quality, we can look at the percent change in summertime nitrogen deposition. So you can see in the graph on the left, we see an increase in summertime change on N deposition in the 2050s, but with some US emission reductions on the right using the Markov model, there is some decrease in nitrogen deposition in the summertime. So in addition to these different science questions that we're asking and trying to, doing different things in these sectors, we also have a stakeholder engagement process. So we're doing that as an opportunity to improve the utility of Earth system models, to develop management scenarios for those land managers and stakeholders, and also understanding which processes to actually prioritize, and also to better communicate output to both stakeholders and decision makers. So we've already held 2 stakeholder meetings on nitrogen management and water supply, and in 2014 we hope to hold 2 more, one on water and air quality, and also one on forests and rangelands. So in conclusion, integrating standalone models from these various disciplines allows us to more comprehensively explore water and land management policies and best management practices in an integrated modeling framework. And Earth system models have included key agriculture-relevant processes in recent years, but there are numerous opportunities to make these models more usable and decision-relevant. So we have finer spatial and temporal scales to improve our decadal scale variability. We have crop models that can handle more diverse crop mixes. And we're trying to have a tighter integration between water, land, and air management activities. And finally, making Earth system models agriculture relevant will necessitate transdisciplinary collaborations. As you can see from my second slide, we are collaborating with people from all across the university and also the country. And we'd like to acknowledge the following agencies: